Okay, let's talk about energy then in simple harmonic motion. After getting the equations of motion, displacement, velocity, acceleration, the next natural step to take is to talk about energy. So it turns out that we can get a lot from the amplitude, the current position of where the body is in its oscillation, because as a body oscillates, the energy of the body trades back and forth between kinetic and potential. So it's either fully extended at a full amplitude, positive or negative, in which case it's fully potential, because at that furthest out point, so if it's oscillating back and forth like this, and this is the midway point, when the body is here, remember its velocity is 0, so there is no energy of motion, no kinetic energy, it's fully potential. And then here, because there's no displacement, x equals 0, and so the restoring force equals 0, and so there's no motion, so A equals 0. There's no, there's no potential energy going on. And so, because U elastic is equal to 1/2 kx squared, and x is 0. There it is. So as it travels from one end to the other and back again, it's trading kinetic for potential, and then back to potential, and back to full kinetic, right? So at any given point in its amplitude, if this is x equals a, and this is x equals 0, and this is x equals negative a, we can know a whole lot about what proportion of the body's energy is potential and what proportion of it is kinetic, just based on its position. So if you remember, the total mechanical energy of a body is equal to 1/2 mv squared, right? And if there's no gravitational potential energy, there's only elastic potential energy, and there's no outside work being done, then we have 1/2 kx squared term, so that's the elastic potential energy. Well, all of that can be condensed down into 1/2 k a squared for simple harmonic motion. So it's only valid for simple harmonic motion. So maybe intuitively it makes sense, but can we prove this? Can we prove this so that we're not just taking my word for it? Yeah, we can. So we have E equals 1/2 mv squared plus 1/2 kx squared, which is equal to 1/2 m, plug in our v from earlier, right? This here. Negative omega sine, a sine omega t plus phi, and that is squared because our term is squared there, plus 1/2 k, and now we plug in our x, so from before, this guy here, a cosine omega t plus phi, and that x is squared. So then you distribute the squares, 1/2 k a squared sine squared omega t plus phi plus 1/2 k a squared cosine squared omega t plus phi. You see where this is going? You pull out the 1/2 k a squared. And you have a sine squared of something plus a cosine squared of that same something, which is equal to 1. So 1/2 k a squared, and that's what we were after. So it's a very useful equation. to simplify the energy of a system in simple harmonic motion, but perhaps an even more useful equation is this one in blue up here. I'll rewrite it. 1/2 mv, the x component, right, linear, plus 1/2 kx squared is equal to 1/2 ka squared. Look at these things that you get to relate here. You can solve for the amplitude given any velocity and spring constant, mass, and position. You can solve for the position given amplitude and velocity. You can solve for amplitude. Did I already say that? Given velocity and position. You can solve for all these things. This in itself is a very useful relation that might help you skip a couple steps in a problem or two. And that's it for energy in simple harmonic motion. It actually gets simpler instead of more complex, which is really nice.